Hey, what's up, guys? This is Chung here. I'm still doing the LeetCode problem today. So I just did like a weekly contest today, and they didn't go very well. So I'm kind of frustrated now. But okay, but we cannot stop our learning, right? So okay, let's take a look at this 979, right? So there's another tree problems here. It's called distribute coins in binary tree. Okay, so what does this problem say here? So you're given a binary tree, right? And on each node, there's like a value which represents how many coins on this node. And there are like nodes that have the values, and for zeros means there's no coins on that node. And there are like n nodes in total, and there are like n coins in total. So the number of coins matches the total number of the nodes in this binary tree. So what you need to make this tree, you need to distribute these coins, right? So that each node will have exactly one node. Mhm. So in this case, right, three nodes, three coins on the root node. You need to distribute one node to the left and one node to the right, right? In that case, each node will be having one here, and you need to return the moves, the number of moves required to make every node have exactly one coin. So for example, this one here, one move down, right, and one move down. In total is two. Here, for example, this one here, starting from here, from the left sub node here, and you need to first move one node, one coin to here, right? And then the next one will be there's another one you also need to move the second one from here to here and then to here, right? So 1 plus 2 will be 3. Last one is this one, right? And so since there's already one node here, you need to move one coin from here to here, right? And then the second one, you need to go all the way here, here, and then here, right? So 1 plus 3 equals to 4, right? So basically that's what the problem means here. So how do we think about this problem, right? So I mean, oh, and one more thing here is to return the numbers of move requires that actually this needs to be like the minimum movement, right? Because you can move one node back and forth, right? For example here, you can move this one up and then down and then up and down for as many times as you want, right? But that doesn't make sense. So this one should be the minimum number of moves required to make every node have exactly one node. Mm, since this is a tree problem, every time when you see a tree problem, I think the first thing come to your mind should be recursion, right? If you were thinking like, since this have three nodes, right? So I have three coins. Maybe I should start traversing from this node and then traverse back here and back here. Um, that will be very, very hard to do, since basically you're doing like you're converting this tree problem to a graph, right? But that will very hard and most likely you won't get the correct result. So how do we think about this, right? And our goal is to make each node balance, right? What by me, I mean by saying balance, I mean to make each node to be one, right? So this is like kind of like a DP problem. So let's say for this, what? Mm, Okay, so let me change this one here. So let's say, for example, we have a 3 here, right? 3 and 0 and 0, right? Okay, so for each node, so basically when every time when we traverse to each node, so to be able to make this node and 1 first, for the node itself, 3 to be able to make it 3 1 3 needs to minus to 2, right? Then it will be equal to 1. But remember, if we have like if but there are like some sub nodes, right? We might need to moving those some of the nodes down there, right, to be able to make those nodes to be like 1 again, right? So which means in this case, let's say, and we need to distribute one node down here, right? So this is gonna be down here and one down here. So so basically for each node, when we see each node, we will try to traverse back to the left and right, traverse to the left and right, and for we need to get each left nodes the coins that needs to be to needs to move in order to make this left node uh to be 1. Same thing for the right one to be 1. So what does this mean? Okay, let me start coding. Maybe that's gonna have better understanding here. So basically we're gonna do like let's see here. Yeah, so basically we need to have like a DFS helper functions here to help us keep traversing down to each node. And I'm gonna call it DFS or called balance to make it balance, right? To make it, I'll just call it DFS here, node. And then we'll have a like answer here, right? It's gonna be integer DFS. So okay, so what do we do here, right? So uh we need to get the left side. How many coins will be putting from the left side? Left. Basically, if node dot left, right? We'll have a left side. First if not node will be returning 0, right? And then left coins will be DFS node left, right? And the right coins will be DFS node right, right? So what does this mean? So every time when we see a node, we'll be using the node value here. If it's 0, so the left side, the coins needs to make this one to 1 is o minus 0 minus 1 will, which will be minus 1, right? Because so for example, let's say there are like four nodes here, right? Four coins here. To make this one this node to be 1, we need to basically distribute three coins to the parent, right? Right. So 4 minus 3 equals to 1. Basically, we'll be moving 3 coins to its parents. And we don't care about what this parent will do, but we know in order to make this one to 1, we need to move 3 coins up, right? Same thing for same thing if it's 0, 0 what means still 0 minus 1, right? Basically it means we need to get one node from the parent, right? That's how we get this left coins and the right coins from left and right. And each time when we get this like left and right, we know that's the steps we need to do, right? Doesn't really matter if it's a minus one or it's a 3, right? Minus one is also one step movement. It's just like in the different opposite direction here, right? So so every time we do a absolutely absolute, right? Because we know the value could be negative, right? Basically, it could be minus one. That's why we do a right coins, right? And then what? So here on each node, so what are we returning here, right? We're returning the current node value, right? Current node value minus uh plus, yeah, minus one, right? That's how we distribute the current node, right? To make this one uh 1, we still also need to minus 1, and then we plus the left coins plus the right coins, right? Yeah, I think that's, yeah, this one should be non-local. Yeah. So basically, what are we returning here, right? So those are the coins we will be needing, will be getting from the child nodes, or will be distributing to the child nodes, right? Plus the current coins on this node, right? And then we minus one. That will tell us since we minus one because I think it's better to minus one in the end because that's how many nodes, sorry, how many coins we need to move back to move up to this node's parent so that this current node can be can have one, right? So we keep doing it until basically we're doing it from top down, right? Every time when we see a node which get the difference, the potential movements, we just keep adding this potential movement to the answer here, and we just return the movement so that this current node can have exactly one coin, right? And then in the end, we just return this answer. Okay, yeah, I don't know if it's a good, probably it's not a very good explanation, but yeah, anyway, thank you guys for watching. All right, I'll be seeing you guys soon.